Okay, YouTube, in this video we're going to look at an example of exponential decay. In our last video we looked at general exponential growth and decay models, and what we mentioned was they come in this package here where we have some amount at a given time, and I actually want to write it that way. Amount at a given time is equal to the initial amount e to the rate times time, and this can always be expressed this way, but in this particular video we're going to look at an instance where k is less than 0, or where we have a decay model. And in this particular example, we're going to look at the example that includes a half-life of a radioactive isotope. So let's read this here. It says this is going to involve a radioactive isotope for which we know the length of its half-life. And I say here that a half-life is the length of time it takes before half of the initial amount of something remains. So basically, if we were to represent this over time, we say time and some amount of something over time, and of course we know that it's exponential decay, so it, of course it looks like this here. But we could say that if this is the amount that we start with here, A0, we would say, well, then half of that initial amount would be A0 halves, and that would be right here. But we could say that if we were to go out and look at the graph right here, it would go ping, and we would look down right here. We would say that this is T, and I don't know how to subscript this here, so I'm going to say TH, where this is the half-life. And so the half-life is the amount of time that has to go by before half of your material remains. And the nice thing about knowing the half-life is that it is a time and amount at that time combination. So if you know these things, then you have something you can plug into this function to go find a model. So we'd say, okay, well, strontium-90, let's go ahead and read this here. It says strontium-90 is a waste product from nuclear reactors. As a consequence of fallout from atmospheric nuclear tests, we all have a measurable amount of strontium-90 in our bones. So here's the deal. It says that the half-life of strontium-90 is 28 years. We're going to put a box around this. Meaning that after 28 years, a given amount of a substance will have decayed to half of the original amount. So what we want to do is find the exponential decay model for strontium-90. So we want the model. Okay, so if I want to write the model, there are two things I need to know. I need to know these. Initial amount, that's the question. Yes, and then we say the rate. If I know these two things, then I can go ahead and write the model. In this particular instance, all I'm told is the half-life information. And so if I'm going to go write a model, I suppose that our model, remember, comes in this package here. We would say the amount at a given time is equal to our initial amount, A0, times e to the rate, which we don't know the rate, and a time. So what I want to kind of suggest is this. Well, we do have kind of a time here. And the question I want to ask is, well, what if I plug this in? What would be true about the relationship between the amount of what I have in terms of material and what I started with? And so what I would like to suggest is this. In terms of a half-life, what we could say in general is this. We could really say the amount at a given time. Well, let's just put it this way. We're going to plug in for the amount at a given time A sub 0, okay, A sub 0 over 2. And what this represents is half of what I started with. And so if I were to say that I started with A sub 0, now I have half of that left, then what I could say is that this would also be e to the k times, in our particular case, 28. So in other words, what we're saying is, if we plug in a time of 28 years, which we were given a time, then what we could say is I would have half of my material left over. And what I've got to tell you is, if we're going to solve for k here, what it involves is dividing both sides by a sub 0. So I'm going to go ahead and write this here. Divide by a sub 0. But what I'm going to tell you is this. When you take a sub 0 over 2 and you divide by a sub 0 over 1, that's really a sub 0 over 2 times 1 over a sub 0, which what that ends up giving us is 1/2. And so what we're going to say here is this. With a half-life situation, you can always say that 1/2 is equal to e k to the number of years. And so in this case, k times 28, I'm going to write 28k. But going and solving this now, we could find our value of the rate of decay. And so what we're going to get is a situation where I'll flip over my light blue here. We're going to take the ln of both sides now that we've isolated this exponential base. And so we get the ln of a half is equal to just 28k. And so if we were to say then k equals the ln of a half all over 28, then we would get an approximate decimal value. Let's go ahead and work in a decimal value here. We would say that the ln of 1 divided by 2, 1 divided by 2, suppose I don't need to write that parenthesis there, 1 divided by 2, and we're going to divide this by 28 is what we had rocking. And so we get negative 0.0248. approximately. 0.248. And so what I want you to notice here is this. This is a rate of negative 2.48%. And so this is negative and indicating that we have a rate of decay. So in terms of our model, we would say that, well, what is our model? Our model, let's go ahead and write this here. At least we know this about our model. Whatever the amount is at a given time t, we know it's equal to the initial amount e to the, and now we have the negative decay rate, 0.024, right, 4 there, 8, and then time. So here is our model that we're going to use here. So for part B of this, it says, suppose that a nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. How long will it take for the strontium-90 to decay to a level of 10 grams? And so what I'm going to suggest is this. What they've given us here is an initial amount. We could write this down. We say A0 is 60 grams. And what they also gave us is some amount at a given time. They say 10. What they want to know is how long. So go solve for the time it takes for 60 to turn into 10, essentially. And so what we're going to do is I'm going to have to bust out another canvas here. Let's see if I can use this guy. Give it a second here. There we go. Okay, so what we want to do is we want to use our model here. We had A at a given time is equal to our initial amount e to the negative 0.0241. Is it 0.024? Oh no, 0.0248 time. And so what we're going to say is that, well, we have an amount left over 10 is what they gave us. And we say our initial amount is 60. What we want to do is go then at this rate and say, well, then what would the time have to be? And so we're going to start by dividing both sides of this by 60 as we naturally would. I'm going to say that this is 1/6 equals e to the negative 0.0248 time. So now here's the deal. We're going to take the ln of both sides now that we've isolated that natural base. So we're going to take the natural log. So we get the ln of 1/6 is equal to negative 0.0248 time. And so by dividing both sides by negative 0.0248, what we're going to end up with is a value of time. And so our exact value is going to be this right here, or as exactly as we possibly can. But what I'm going to do is I'm going to write approximately equal to. And again, we'll definitely want to find this on the calculator. So we say the ln of 1 divided by 6. We're going to take this divided by a negative 0.0248. And what we end up with is 72.248-ish. So 72.24. I'm just going to write 2. And this is time. So when we say time, we're going to say years. And as a matter of fact, what we were discovering was the amount of time it would take for 60 grams to turn into only 10 grams of this strontium-90 that we find here. Cheers.